Okay, so if you Google the law of energy conservation, you'll probably see um, that in an isolated system or in a closed system, the total energy remains constant. So I just wanted to take a little bit, a few different demonstrations of what that would look like in certain systems and sort of how that shows up in some different examples. So if we have this person on a skateboard here, we can see on these graphs over here on the left side of the screen, we have kinetic energy, potential energy, thermal energy, and the total energy. We'll talk more about what these different types of energy are, although some of you all probably have backgrounds or like know from previous classes or experience what these different types of energy are. But for now, all we need to know for this is that kinetic, potential, and thermal energy are three different types of energy, and the way that the total is being calculated here is just the sum of all of those three different types of energy. One last note before I start getting into this also is that there are more than just these three different types of energy. There's chemical potential, and sound and light energy and nuclear energy, but we're just going to use these three as sort of the three types of energy that are changing or that are contributing to this total in the system. So if we let this skateboarder start falling, you can see the kinetic energy increases, the potential energy decreases, now increasing again. But as they move through here, and we can go normal speed for a second, you can see the total energy isn't changing, which is exactly what the law of energy conservation states, is that for a closed system, which right now this is, the total energy is not going to change. Now, if I introduce friction in here, we'll start to see this buildup of thermal energy, and you might notice that the skateboarder is not going quite as high as they were at the beginning or from where they started from. And slowly but surely, this thermal energy is taking up a bigger and bigger piece of this total, but the total energy in the system is still remaining the same total, even though this kinetic and potential energy, those are both decreasing. Now, just to put numbers to this, the way that we've started to solve problems, and there will be a later video on how we really solve problems using energy conservation, I wanted to take a second to just put some numbers to this. So let's say we take a second to pause this, and up here, this skateboarder has a total of 3030.2 joules, and we'll remember that number, 3030.2 joules of total energy. They have no thermal. I haven't turned friction on yet, so there's no thermal. And then they have a whole lot of potential and a little bit of kinetic energy. Now, if I let this play for another second, you'll notice the potential has decreased. It used to be right around 3000, and the kinetic has increased, but this total 3030.2 still remains the same. So this becomes really useful for us when we want to know maybe how fast the skater is going to be going down here, or at their fastest at the very bottom even of this sort of skate park or of this ramp. And we can do these calculations using maybe a height. Let's say that we wanted to know how fast they're going to be moving at 0.38 meters up for whatever reason. If that's something that was of interest to us, then we could use this idea of energy conservation. We could calculate a potential energy and figure out the missing kinetic energy to get our total the same, and figure out what these different sort of design variables could be if we were the engineer designing some ramp or making sure that this was a safe roller coaster or any other things that we'll see in future videos. But this total energy is going to remain constant no matter where I put this. You'll notice that their total energy is still the same, 3030.2. Now, one additional way to see this is through a fairly complex looking graph. So what this is going to show is these different energies, kinetic, potential, thermal, and then the total energy, at these different positions. So over here at the top is 0 meters. You'll notice that the skateboarder was starting right around like 0.5 meters to the right of this 0 line over here. So that's where our graph's going to begin. And you'll see what this looks like. I'll play it on slow first. Okay, so that's one complete cycle, and I just want to point out a few things. One, the kinetic energy increases. It goes from 0 up to like maybe 2,000 joules about. And then the potential energy does essentially the opposite thing. We see these almost like a give and take between the potential, which is decreasing, and the kinetic, which is increasing. And then once the skateboarder gets over this midpoint where they start going up into the air again, they sort of switch roles. So now the kinetic energy starts decreasing when they're on their way up and they're slowing down, and the potential energy is increasing. But the part where conservation comes in is the fact that this total energy, again, is staying constant this entire time, and that is always going to be the case. So I'll let it play back again, and you'll see the exact same trend. Again, this total energy represented by this yellow line up top is not changing. It's staying at the same, somewhere around like 2,000 joules, it looks like, the entire time, while the kinetic and potential energies are transforming between each other. The thermal energy, in this case, without friction, is not going to affect anything. I'll, in a second, show what this graph looks like when we introduce thermal energy into the system. But for now, we'll just take a second here and think about or note for ourselves the idea that total energy in this system can remain constant, but the energy forms can take different types, and energy can transform between these different types of energy. Now, if we introduce friction into this system, I'll still play it on slow, we should probably see some increase in thermal energy. We see a slight increase, and you'll notice before, our potential energy at first was taking up all of the energy in the system. So all of this total was from this potential. And now that we have some thermal over here, even though the skateboarder stops at the top, the potential energy doesn't quite take up all of the energy in the system, right? Because we have some thermal energy occupying some of this total as well. And we'll see that trend continue to sort of become more and more dramatic. So now at the top, our potential is taking up even less of this total, and then even less, and the thermal keeps increasing while the potential and kinetic at their maxes decrease until, just like we saw in the other example, all of this energy in the system becomes thermal because friction is acting to sort of take away some of these other types of energy and convert potential and kinetic into thermal energy. One possible other way to think about this is as sort of a piece of a total. So with this pie chart visualization, we can see that the total, like the pie of total energy is not changing, but the amounts and the relative proportions of kinetic and potential energy can be changing this entire time, even the total isn't changing. Now, one last comment on this is that if we introduce a little bit of friction into this system and we let this play, if we only were paying attention to our kinetic and potential energy, it might look like this system is losing energy. Because if maybe I'll let this play on normal speed, you'll notice it looks like this skateboarder is, and they are, going less and less high up this ramp each time. And so it would look almost, if we were just watching this and we didn't have these energy graphs over here, it might look like they were losing energy in this system. But in reality, energy was being transformed into this different type of energy, different form of energy. And it's very possible also that energy could leave this system, which would be not a violation of energy conservation. It would just be simply a demonstration of an open system or a non-isolated system where all of the energy maybe is in the universe remaining total, but in this system maybe is changing because energy could be leaving. Maybe instead of just heating up this ramp, or depending on how we define our system, maybe it is heating up the ramp and we're just seeing the energies of the skater, and energy is just leaving this system, but not necessarily being created nor destroyed, and so energy conservation isn't violated. But the main idea from all of this is just that idea that energy conservation demonstrates this fact and this law that in a closed system, and if we consider the universe a closed system, the energy in the universe and in a closed system will always remain constant, even though energy can take different forms. The total will remain constant.